Let me start with the video again. This continuation of this lecture is all about the design of thermoelectric cooling system. Generally, whenever we talk about a thermoelectric, we concentrate on only the Peltier. It is real. Peltier, working with the Peltier is real. There is no two things about design of a Peltier. Now, if you see this other monitor which is mentioned here, this is taken directly from Meerstetter site. Probably it is from Swiss, looking by this thing, but now we do not know where exactly they use all these things. One of the first thing is saying it is a big system. First of all, the most important point here is to estimate a load. Without the load estimation, first of all, estimate the heat load of the object to be cooled. Then define temperature, working range of object and heat sink. So, if you can see my face again, the issue being we have a very interesting thing. We have a heat sink which is supposed to take heat from the object that is to be cooled. So, heat sink looks like there is something about infinite. So, by definition it has only a finite capacity of absorbing the heat. After that it tends to rise and then it will transfer it to the ambient or next cooling medium. The cooling medium can be normally simple air, occasionally liquid. So, the temperature of the heat sink seems to be a very critical parameter which you need to decide approximately. If the heat sink is cold, it is not doing any purpose at all, because a cold heat sink cannot transfer any heat to the ambient. Let us say the ambient is around designed ambient is around 40 degrees centigrade. If the heat sink is already at 40, it can't transfer any heat to that. So, we have this peculiar thing being the heat sink final temperature has to be higher than the ambient, only then it can transfer heat. But then if the device, that profile is hot, it can't pick up heat from the object to be cooled. So, somewhere you need to fix the two parameters. So, generally a good starting point is start with an average. Take the average outside. 25 degrees and all are very standard, but generally things are made such that they are expected to work at a more reasonably good ambient which is there. In the tropics where we come from, around 40 seems to be a reasonable thing. So, I generally start with an ambient or 40 degrees centigrade, and now any heat sink which needs to transfer heat to 40 obviously has to be higher than the object that has to be cooled, which is probably at 70. So, if you take an average between 70 and 40, it will come to around 55 degrees. So, if you can make a heat sink which is typically it can reach around 50 degrees centigrade, considering its total mass, considering the convective heat transfer which it can go, we have partly started on our business. Now, if you look at the the monitor what they have given, one of the thing is estimate the heat loads. Okay. Important is the amount of heat to be absorbed from the object by the cold surface of the thermoelectric module or Peltier element in watts. Depending on the application, there are two heats, power dissipation and convective and conductive thing, and dynamic. So, we need to define a temperature saying to object temperature. Two design parameters are important when outlining a thermoelectric cooling application. Okay. Object temperature, cold side temperature, heat sink temperature, hot side temperature. So, we need to think about it. The difference between TO and THS is known as the delta T, and see, suddenly we are in, we end up with this also. Ambient temperature delta T minus the object temperature. So, you see here, then after that, which comes to, I suggest you go to the site and try to read about this whole thing from the top to the bottom. How do you choose a controller, and how do you choose a element? A controller is about regulating the current applied to the Peltier element according to the desired temperature of the object. But since we are electronic engineers, chances are you would want to build your controller. It is nothing but a constant current source. They also sell controllers, but because of various operational or your packaging issues, it is possible for you to probably build your own constant current source. Otherwise, buy the whole thing from them. So, if you go down here, we have things which are listed, which works with 9.6, all this 2130, dual channel is there. So, controller product page is there. Now, it is necessary to add some reserve when dimensioning the heat sink to avoid that its temperature goes too high. Following diagram indicates, and so on. If you go down, heat rejected, heat transported versus this thing. We have several types of curves here. You have seen here, first of all, when there is no temperature difference across the sides, that is, you are able to elevate to height uniformly to the temperature difference which is at the max. So, all the curves are plotted here, seen here, QC all the way to these things. We can use this plot to estimate resulting heat sink based on the amount of heat transported even before choosing a Peltier element. To calculate thermal resistance, we assume a realistic value of delta T at the heat sink. Since we do not know the real QH yet, we estimate by the above graph, find the ratio, choose a desired temperature difference, and so on. And then finally, we come to this fan thing. This I suggest I will just write it, I will try to read it along with you, but it is peculiarly, unless you have gone through it yourself, it will not make sense. Not very different from learning cycle balancing or swimming. You have to get yourself wet, and unless you do that, no simple way of learning either of them. Here they have given here, if you see clearly, we have just as a working example, there is a maximum cooling capacity we require is about 10 watts to be cooled to 0 degrees Celsius, 0, and the room temperature is 25. Why 25 is taken is, this is the standard condition in which most testing takes place, and then as I said in your practical example, you can probably go up to 40 degrees. 40 degrees is a reasonable thing, and generally wherever we use our equipment, probably the ambients are all controlled, and just around the electronic equipment it is relatively easy to maintain 25, maximum it can go up to 30. The room itself can be a little higher. The temperature difference between the cold and the hot side of the Peltier is 30 degrees. It is important to remember that it would be incorrect to calculate delta T as difference between ambient air and the desired optic temperature. You have seen that, no? So, our goal is to find a Q max that is large enough to cover the needed QC and yields the best coefficient of performance. In the performance versus current graph, we locate the maximum of the delta T 30K curve at a current of 0.45. Ratio should not be more than 0.7. You see here, this is where the current should be. If you exceed it this side, we have a little problem about it. There is an inherent heating inside. So, the actual current what we need to draw should be way below this, somewhere, no, more like I would prefer this. In the end of the example, he will tell you how to come back here. So, now here you see here, if you go using the factor for the current, we find the heat pumped versus current graph. QC by Q max is equal to 0.25. Seen this here. .45, you go to 0.25. Heat pumped versus current. So, you see now QC by Q max, no, is typically around 0.25. We can calculate the Q max for the Peltier element by calculating the saying. This is the first critical step. Taking an element which is higher is a very prudent way of working. Anything higher than this will be much better. Even if it's a 50 or 60 or 70 watts, it's way better than just taking something which is a little lower, because in the end you may end up with wrongly sized components, and then we end up with more and more thing having to come back here and work with it. So, typically I will stick to this 0.25 and I will stick to this 40 watts. In the performance which current graph, we find COP is 0.6 for our previously read about this thing. This allows to calculate QC by QOP is typically 16.7 watts. Peltier element manufacturers offer a wide range of elements. In their product line, we look for an element of QC max of 40. As we have a temperature difference of 30K, a single stage Peltier element is sufficient. We choose a Peltier element with Q max 41 watts, intentional, because it is 40, no, he has taken 41 watts. Delta T can be anything, I max 5 amps and V max is 15.4 volts. The operating current and voltage are calculated. So, we come to 7.42 volts, in which the Peltier element has to be operated upon, and typically I will be around 2.25 amps. Based on the calculated values, we choose this thing. The second part, we need not worry too much about it. And you see here, usually heat rejected versus current, again we have all this saying heat sink thermal resistance should be approximately 0.2 degree K per watt. We need a heat sink, the thermal resistance smaller than 0.2 degrees K per watt, which is tough, it is not easy. Normally we come to things which are 1 or 2 degrees centigrade per watt. So, hence we will be forced to real system, and iterating through the design steps is necessary to determine the optimal system parameters. In this, important thing is only a starting point. In the starting point, we have come across, you read these things again, you go to the Mearstetter website and you will be able to see all these things saying critical thing is 0.2 degrees Kelvin per watt. Tough, extremely tough. And we come to the, just I suggest you just read it through. When you are looking for heat sinks with that typically very small what do you call thermal resistance. One of the other important thing is how do you measure the temperature. Obviously, we need to have this different type of you have seen this here. We have a several types of measuring object temperature demands higher pressure and a larger range. We suggest use the PT 100. We are able to measure between below this thing. We may require PT 100 the probes are required. If the temperature gets too low, NTC probes can't be used as the resistance value gets too big. So, here one more thing is often we have directly small chips which are taken from any of the standard websites which you can continue to use it, but by definition invariably we are expected to use 4 wire sensing because we are dealing with thermal parameters, and then all wires also have a temperature coefficient, and we are talking about small changes 0.1 0.2 millivolts change. This is sufficient for disturbing all the readings. So, invariably they have the 4 wire sensing this thing. So, you go to current carrying and voltage sensing electrodes are used. More information about 4 wire terminal sensing is given there. If I click on it now, it will now I will see whether I can open it in a new tab, let it keep opening at the back. Then we have power supply, and then you see we have all these things here. At this point, let me see if you see here a little about the 4 wire sensing is used, meaning what is the actual current and what is the voltage across. I suggest since you are electronics engineers, you need to probably read it up yourself. So far, this is only a simple worked example which is taken from here. See here, if we are looking for things like that 0.2 degrees centigrade per watt, we end up with this powerful heat sinks. It is not easy to manage with this. And now, how do you use this heat sink and attach it to your device to be cooled? So, obviously, whichever way you look at it, if I put the Peltier here and if I put the device here, I still have a lot of these hot things are there, and one Peltier I can do. Is there a way of me to put a Peltier on both directions? So, I will give you an example of see what an attempt we are trying to make here is I am trying to design see there I have taken a 40 mm by 40 mm Peltier module, which by all other calculations and typically that is what is occasionally used in it, and saying now is there a way of for me for attaching 4 of them. Seen here something has been made here which is exactly I am trying to attach 4 of these on 4 corners like this. The moment I have it, and the dimensioning also has been done such that from here to here it is 40 mm, is approximately 40, this is 40 and this is 40. Total I have 120 mm, and miraculously this fan is also 120 mm fan. Instead of my directly just putting it here like this and then trying to live with it, I now try to see whether I use this portion with a small square, what do you call, a cubicle, or what do you call, elongated ellipsoid with a cross section, where all the four sides of it are packed with thermoelectric coolers. The advantage of that for me is, now I have a cavity in the middle which is typically like this. Understand, no? You see the little squarish appearance, and if I can make the whole thing by directly using the heat sinks, it is possible to make a small cavity inside which has lowest overall mass of it. What you see here is the outside of the, you understand what you see here now, here to here is the outside, inside here now come the Peltiers, and I have a cavity typically. If I you see there, you see that small square which I have drawn inside, the thickness represents the thickness of the Peltier element. Now it is for us to decide whether what happens to that corner. If each of them is this much, do you make it overlap here, or you make it overlap here, or just leave a gap in the corner? I would prefer you make some arrangement by which you attach one more heat conducting thing, typically an aluminum tube or something, and all your items now should be inside that aluminum tube, and the moment you are using a square tube, we end up with a corner which has a little gap. So fill the corner with some insulating material. Typically you can continue to use something like, depending on the temperature, if it is not likely to exceed 70 or 80 degrees, you can maybe pack it with polyurethane foam pieces. You probably require something is around 4 mm by 4 mm. You carefully what do you call, sculpt a small piece and try to push it in the corners. So getting back, you have a square, we have a square what do you call, a tube extrusion which is 40 mm by 40 mm. 4 corners we have the 40 mm Peltiers stuck with it. Right now I will say the use sticking because there are heat conducting. Then the corners you can now put your whatever that thing, typically a polyurethane, rigid polyurethane foam, which is the normal insulation we use. Moment you put it now, if I for my argument I will take that 4 mm is the thickness of the Peltier. So 40 plus 4 plus say 4, 48. So typically I can now start looking at it and see how big or how small this heat sink needs to be. Right now it is 40, we can afford to make it a little bigger, maybe 50 mm can be bigger. Now obviously the very simple way of making something is make all the heat sinks about equal. Only thing is right now the length has not been yet fixed. And now just to put a fan, we have an advantage now in that once you have a fan here, you also will have a neat area to start your work. You see here, this is typically a fan outline, and then this is the actually the force, I am sorry, where the air is getting blown inside. We need these dimensions for various other things. The moment you have it, suddenly I notice a very important thing. You see, I still have a little more place here. Is it possible for me? Why let that wind or the cooling air go wasted in that small sector? Because if you consider all the 4 of it, no, it is still significant. It will contribute to around extra 10% of the total blow that is possible, and the flow can be regulated properly. Unless we block this area, the chances are all the air will escape into this corner. This is where our product design issues come into picture. So, I will now start working and seeing what else can I do about it. So, one estimate has been here, no, made here. You see there, what I will do for the purposes of this thing here, I will now switch over to another drawing which I have already created, and oops, sorry. You see here. See, what has been done here is our little bit of work. See what I have tried to do. I feel this is the slightly innovative part of any of our product design. Hence, I feel compelled that I should share with you. So, what has been done is, in the normal course I will just keep only one of them on and see how things go. See what has been done. If I go to the plan view, looks fine. We have the corners and it looks okay and so on like that. Now, we come to the much more or equally critical way of dealing with this whole situation. Coming back to the heat sink design, if you remember, I told you why all these heat sinks have been made this way. You have a little, what do you call, little fat thing, and then after that we have this limb which is slowly getting tapered here all along, and then we have each of them fins is a tapered fin. How it has been done is, total they have tried to calculate what is the cross sectional area of the heat to be going out, and with the temperature which is actually at that point, and all the way in reality the heat sink at the tip should be about the same temperature as at the base when it is being cooled. That is what is equivalent to what is called the fin effectiveness. See, the fin will not be effective unless the whole fin is at the same temperature. And how do you make it at the same temperature? When you have a blower cooling it all the time. So, the rate of heat conduction should be balanced to the rate of heat convection to the ambient. And now, I have tried to put another what you call unwanted thing here. We have a corner here, you have seen here. We have this corner now. Now, when we have two of these devices, how do I, now what do I do? If I put one more device here like this on this corner, that will not have enough of a base to conduct away heat to the tip of the fin. So, what I have done is, which I feel, it is just a matter of, I am trying to get it fabricated. Now, whether this thing is really universal or not, we will come to it later. See what has been done. Each of these heat sinks, one half has been milled out. Why this is on the corresponding side, one more half is there. So now if I go back to the back of this heat sink, it is just a, I mean at one point no, you may call it a gimmick, and at one point I feel this is how we try to build a bit of IP content into that. So a lot of these commercial heat sinks are, maybe people try like this. So we have here this part of it is fully understood, there is no problem. Now part of this flow in this corners can be used by putting a heat sink here, and to make them symmetrical, one half I have attached a base to this here, and the other side I have the other half, in which the other half is offset and kept here. Advantage being, now when I keep one over top of the other, I have a gut feeling or an intuitive feeling that all of them will probably form a nice cute feature like this. Now you see here, when I put all of them together, I have the advantage of this center portion, top portion is covered by this part of the heat sink, and bottom portion is covered by this part of the heat sink. The advantage being, now I have this corner thing. Yes, I am happy that you have noticed it, that saying, sir, but what is this doing here in this corner? And then if I see in this plan view, a lot of this thing is a waste, is it not? Yes, most likely no, a lot of it is probably an overdo, overkill, and too much of effort to go into this. If I had control on the profile extrusion, probably I will also ensure that at this point the spacing is a little larger. You understand, no? The spacing is a little larger, to the extent now when we look down on this area here, when we look down on this area here, you will have less of any interference from adjoining heat sinks, and then I have what looks like a neat rangoli. The issue here is not rangoli, the issue is if I now spend what you call enough effort and time and coming up with a heat sink design like this, most likely I can have a IP in it, others can copy it, no issue about it. I will now optimize it by putting it through some sort of a simulation. The simulation is, it will take care of each of these devices, and then a full fledged QFD probably running on MATLAB or other code is required to solve these problems. Having done this, now I notice, rather I would like you to, I would like to point out to you this heat sink I will take up. Seen this? Maybe there is a chance for you to, I am not bragging saying this is the only way to do. Now you see here, and probably a little gap, and I will use all these devices and the place here to introduce that small PT100 or other type of tiny, what do you call this, thermocouples, which can be, probably you can drill a small hole, insert it inside on the bottom surface, and mind you, inside I have Peltiers, and inside those Peltiers I have the aluminum tube, and if you remember, I have the corner still. I have a little access to the corners here, and once I have access to the corners here, either I can leave a gap between these two heatsink, top and bottom, so that I do not need to drill the heatsink in any way. Alternatively, I can make a small half circle, a semicircular groove here, by which it can go inside and directly it can take in one of the corners. And then when I have that 40 by 40 conductive tube, I have access to all the 4 corners, and then I can put my, what do you call these, thermistor elements wherever I want. I can keep them one in the corner, one in the bottom, and all that. So, I have a way of now directly measuring the temperature on the full profile which is available for me. Having done this, all I need to do is now, I have a fan. Now I need to take that little, this thing, is it blowing or anything? Earlier itself I have told you about it. It is much convenient if you put always cold air to be sucked by the fan, and fan sees the cold air only, and afterwards you have our heat sinks and things here. Only for purposes of illustration, I will show you here. Imagine we have one device here with a little bit of, for the flow to develop you require at least 10 millimeters, then only the flow develops freely. Alternatively, it will start making too much of a noise, which is incidentally, which is the same principle in which air raid sirens work. Air raid siren works by closely, these things here coming close to it and making a terrific racket. If you just leave around 10 millimeters, the racket won't be there. Imagine you have one heat sink here, and then something double the height, one more will be there. And as you said, these things will be straight long, but this portion will be coupled to this, and so on. And in principle, the top can be left open. And you can try your best to see if you can now provide a chute or something, leave a little gap, leave it absolutely open. Further, if you want, in case the flow is not sufficient, just add another fan. Once you do all this, in principle, the idea should be that the heat sink itself should be something which is fresh, taken off the shelf, and something we do a little bit of modification only for mounting it together. The very fact that we have so many types of heat sink shows that there is always place for one more design, which I feel is relatively easy here. So today, for this session, allow me to stop here. I will try to continue on this next time when I take, then you can read it here. You will again see the same view. Then I have a fan which is attached to the top fan at the bottom, and then in due course, after the milling and all is over, probably I will try to show it to you. So I will stop here today. Thank you.